Hi everybody, in this video we are going to find the exact value of tan or tangent of the angle 7 pi over 12 and we're going to show all work. I'm actually going to do this problem two different ways. One way using the traditional tangent angle sum identity, and in the other way I'm actually going to do it using sine over cosine, so the sine angle sum over the cosine angle sum. And at first it would appear that each approach gives you a different answer. However, if you fully simplify both answers, meaning that your answer should have no radicals in the denominator, you also shouldn't have compound fractions or complex fractions. You should have a nice clean fraction rationalized. And if you make sure either approach, the answer is fully simplified properly, they should be the same answer. All right. So even if you just did it one way, I really suggest you pay attention, follow along, copy down the other one, and think about which one you think is better for you, where your strengths and weaknesses lie. Maybe your struggle is going to come in the form of simplifying. And I know the first lesson I did with my pre-calc classes this year was simplifying radicals. And I wouldn't really call it a lesson so much as a review, because you should have learned to do that over the years in the past, but we all know not everything sticks, so hopefully after all this it does. So let's get started. First way through, what I'm going to do is I'm going to do the kind of panic approach where maybe you only memorized sine and cosine stuff, and then I'm asking you to do tangents, so you're like, I'll just use what I know. That's fine. You can definitely do that. Now, another issue that some people may have is like, what the heck is 7 pi over 12? It's not in degrees, so it makes it a little bit harder for you to figure out which angles should I use to help me figure out, what the exact value, a non-rounded, non-calculator answer to tan 7 pi over 12. What angles should I use to either add or subtract, and in this case we're going to do addition, to get 7 pi over 12. So first place you should start is think about your quadrant 1 angles. We obviously have 0, we're not going to use 0. Next we have pi over 6, we also have pi over 4, and we have pi over 3. Okay, 30 degrees, 45 degrees, 60 degrees. All of these angles can be written with the denominator of 12. In order for this to be rewritten with the denominator of 12, we would have multiplied the top and bottom by 2. 2 over 2 is 1. You're allowed to multiply by 1. Multiplicative identity, all is grand. Okay, great. There we go. Next angle, pi over 4. If I wanted to rewrite this with the denominator of 12, I'd multiply by 3 on top and bottom. 3 pi over 12. These can give me 1 pi over 12 if I subtract. These can give me 5 pi over 12 if I add, but no luck with the 7 yet. Keep it moving. We would have to multiply this on top and bottom by 4 pi over 12. All right, these two could also give me 1 pi over 12 if I subtract, but they could also give me 7 pi over 12 if I add. So winner, winner, chicken dinner. So I'm going to make this alpha, and I'm going to make this beta, and we are going to figure out the tangent of alpha plus beta. And like I said, I'm going to do this as if you panicked and you were like, oh no, I didn't memorize the tangent formula. I'm going to use sine and cosine instead because those I memorized. All right, let's do it. All's good. So we start by writing down what we're about to do. And now we're going to do it. Let's go. The sine keeps the same sign. The sine stays the same. But the trig function, pay attention to these tricks I'm giving you to memorize. You're welcome. The sine stays the same, but the trig function changes. So sine alpha, cosine beta. Sine keeps the same sign, plus. Now, I need the other combo. Cosine alpha, sine beta. All right? Over cosine. Couple things. Got a few tricks for you right now. Cosine. co-workers, co-pilots, co-presidents. You know, you're together doing something, you're buddies. So we're going to buddy up. It's going to go cosine, cosine, opposite sign, because only sine keeps the same sign, and then the buddies, sine and sine. Obviously, alpha, beta, alpha, beta. Another trick that kind of exists within here, hidden, you have the cosines, you have the opposite sign, and you have the sines. So you have a little hidden cosine within. You're welcome. One of my students years ago made that one up. All right. Sine alpha, cosine beta, cosine alpha, sine beta. Oh boy. Here we go. Alpha is pi over 4. So I'm just going to do a little side writing so no one gets lost, okay? People who struggle. Alpha is pi over 4. It's also 3 pi over 12, but it's the same angle. What's the sine of pi over 4? What's the cosine of pi over 4? These are things that you should know in your brain. You should know them by heart. You should know how to get them from the unit circle. You should know how to figure them out if you forget them. Sine and cosine of pi over 4 are both square root of 2 over 2. Now, beta, which equals pi over 3. What is the sine of pi over 3 and what is the cosine of pi over 3? So pi over 3, tall and skinny like a tree. It's the pi over 3s are up high. Sine, up a lot. Root 3 over 2. Cosine, over a little. 1/2. Okay, and it was a little squashed in the end there. So let's fill in now. Again, you're going to have parentheses. You will not be writing sine and cosine anymore. Once you evaluate and you find the sine or the cosine of something, you don't have those words in the problem anymore. They're gone. Just like when you take the square root of 100, it doesn't equal the square root 10. It equals 10. The square root's not there anymore. So don't write it. Now, filling everything in, right? Sine of alpha, cosine beta, plus cosine alpha, sine beta, over cosine cosine. Cosine alpha, cosine beta, minus sine sine. Sine alpha, sine beta. Okay? Filling it in. Sine alpha, cosine beta, cosine alpha, sine beta. Denominator, cosine alpha, cosine beta, sine alpha, sine beta. Now, if you want to be voted off the pre-calc island, the best way to do that would be to start crossing things out from your numerator and denominator here. You will be voted off the island faster than you can say trigonometric. And I know some of you can't. It's okay. All right? No, no, and no. You cannot reduce a fraction by crossing out pieces of a sum or a difference. You can only reduce when things are attached purely by multiplication and or division. All right, so none of that's happening. Let's clean up a little bit more. If it were that easy, everybody would do it. Not a thing, okay? That becomes root 2 over 4 plus that becomes root 6 over 4. Root 2 over 4 minus root 6 over 4. It's an awfully long fraction bar for no reason. But I'm going to leave part of that there. I'm going to start cleaning this up some more. There are other simplifying techniques that you should have learned over the years between Algebra 1, Geometry, Algebra 2, maybe even before that. One of these steps is, I don't want to have this compound fraction right now. You look at all of your denominators. If this were just the number 5, that denominator would be a 1. Look at all of your denominators and you determine, if I wanted a common denominator, what would that common denominator be? The least common denominator. It wouldn't be 1, it's just the smallest number you could turn them all into. Some of you need to work on that. You need to go back to, I think it was the sine, graphing the sine function, maybe the on your own example. That was a good place where I gave a lot of explanation. And then I'm going to multiply my numerator and denominator by 4. Think smarter, not harder. We're going to reduce as we go. Okay? What happens? 4 to this, the 4's reduce. What's left? Just square root 2. 4 to this, because we do distribute, right? Reduces, and we're left with just square root 6. Over 4 and 4. Same thing happens. Root 2 and minus root 6. But we are not done yet. I know, I'm sorry. We're not. We need to finish rationalizing our denominator. So all we got rid of by doing that, we got rid of the compound fractions, like the fractions within the fraction, the inception of fractions. Now we need to rationalize. We have radicals in our denominators. These are irrational numbers, non-repeating, non-terminating decimals. We do not leave those in our denominator. We're going to rationalize, to make rational, this irrational denominator. Think about the words. How do we do that? No, we don't multiply the top and bottom by radical 2. No, we don't multiply the top and bottom by radical 6. No, we do not multiply the bottom and top and bottom by radical 12. I hope that somebody out there remembers between geometry and algebra and earlier this school year that you would multiply the denominator and the numerator by the conjugate of the denominator. Write it down if you didn't remember. This is where you take your own notes. So when you go to college, you could do that. You multiply the denominator and, I'll repeat it, the numerator by the conjugate of the denominator. And if you don't know what a conjugate is, then you have not been paying attention. Here we go. Lovely. How do you multiply that numerator? How do you multiply that denominator? Well, you distribute properly, my friends. And this type of example, that would mean you can use the mnemonic device FOIL, first, outer, inner, last. So, guess what I'm going to do? Show you all the steps. You're welcome. Let's draw me some long fraction bar. Hopefully that's not too long. First times first. Okay, guys, it's a tough one. Root 2 times root 2. That's the same as root 2 squared. The square root squared. They're inverse operations. They get rid of each other. Square root of 2 squared is 2. Or it's the square root of 4, which is 2. Stop writing 10 steps. You should know that by now. There you go. Okay. If not, it's okay. Your secret's safe with me. Just fix it. Fix it. Don't leave the food in your teeth. Root 2 times, right? Because if someone tells you you have food in your teeth, you don't just leave it there. You take care of it. So if you make a mistake in your work, you don't just leave it. You go back and fix it. Root 2 times root 6. Earlier, we said we could not add things like that. We saw that in another example, sine of 15 degrees. However, you can multiply them. Square root of 2 times square root of 6 is going to be, positive square root of 12. That's outer. Now the inner, also positive square root of 12. We will be able to add those in a moment. Last times last, very similar to first times first. Square root 6 times square root 6 is square root of 36. I don't know why I was going to write that step for you. You guys don't need that. I don't need to treat you like babies. 6. Lovely, lovely. Then from there, we do the denominator. They're conjugates. That means the outer and inner will cancel one another out. And you will only have to deal with the first and the last. Just be careful. Watch the sign of the last. First times first, it's going to be very similar. It's 2. Outer is positive root 12. The inner is negative root 12. Bye-bye. negative root 6, positive root 6 is minus square root 36, which is minus 6. So minus 6. From there, a little too aggressive with my fraction bar again. From there, 2 plus 6 gave 8. Square root 12 and square root 12 is really plus 2 square root 12. The square root of 12 can be reduced. 12 is the same as 3 times 4, but the 4 is 2 times 2. Since 4 is 2 times 2, 4 is a perfect square. What's the square root of 4? 2. This is 2 times 2, or 2 squared. So we're going to use that to simplify in the next step. All over. Down here it's negative 4, and we also spoke about earlier this school year in this course that we don't leave our negatives in the denominator, similar to not leaving a radical. Next, 8 plus, that 2 is already there. Another 2 comes out to join it because the square root of 4 is 2. And then what's left is just the square root of 3 over, there's that 4, and the negative, I'm going to pull it, very important, right in front of my fraction bar. I don't just let it float in front of the 8, and I'll explain that a little bit more in the next step. Then 8 plus 4 root 3 over 4, here's the parentheses. That minus, when it's in front of the fraction bar, it really means it's also right there, and it would distribute to the whole top. Most of the time you just have a single expression in your numerator or denominator, so we don't have to get too crazy there. Now, the reducing. If you want to rewind and listen to what I said about reducing earlier and see that what I'm saying will still apply, I cannot just reduce like those 4s and call it a day. It really has to reduce from everybody. I said that it has to be purely attached with multiplication and division. I could factor that 4 out of the top, and then I would have a negative 4 parentheses 2 plus 1 square root 3 over 4. And then that 4 and that 4 would reduce. Okay? It's the same as doing the pretzel. The 4 root 3 is all attached, but the root 3 doesn't get touched. It's just coming along for the ride. So what happens now, just for the sake of saving a little bit of paper and not going to a new sheet, I'm just going to wipe that out. And we will have the negative parentheses 8 and 4 reduces to 2 plus 4 and 4 reduces to 1. You don't need to write it in this case because we're going to write the next term. Square root 3, and it's all over a positive 1. So your answer is fine like that. Or if you distribute that negative and open up those parentheses, it would also give you negative 2 minus the square root of 3. And both of these answers are the same. They're both fine. It doesn't matter. I don't think you should have an issue finding it if it were a multiple choice question or something like that. And that is the end of that example. Just trying to make sure it all shows on the screen. So I understand that this was a little harder with the radians, a little awkward with the fractions. You just really need to take your time and just abide by the rules, just follow the rules is really what it comes down to. All right, so this is the end of the approach using sine over cosine. That might be a lot more work than the approach using just tangent. So you're going to have to click through now at the end to the tangent video where I use the rule for tan alpha plus beta, the purely tangent rule, and find out if you think that one's easier or if you think that this one's easier. You should get the same answer either way, so let's find out. If you did get the right answer, whether you did it this way or the other way, you can give the video a thumbs up. And if you got the wrong answer or a different answer or you don't know, give the video a thumbs down, okay? See you in the next video.